so so I will it's a pleasure for me to introduce the speaker of today, which is Daniel Íñiguez Pascual, who is Daniel did his bachelor thesis at UAB and his master thesis here with Diego Lopez and Daniele Vigano, and now he's doing the PhD here at the Institute with Daniele and Diego, and they talk us about the INFP emission of the pulsars with synchro-CURVATURE radiation, synchro-CURVATURE radiation moments. So I leave the stage to Daniel.
Okay, thank you. Thanks for the presentation. Hello, everyone. My name is Daniel Íñiguez Pascual, and today I will talk about a variative model that has been developed here at ICE in the last years, and which I've shown in my bachelor thesis, and I work on my master thesis, and now as a PhD student. This model tries to explain the high energy emission of pulsars concerning the synchro-curvature radiation. First, I will start with a brief introduction about what high energy pulsars are. Then I will present this variative model, and then after that I will show the results of spectral fitting of the population of high energy pulsars with this model. After that, I will move to a more numerical side of our project, in which I will introduce a numerical improvement done in the last year. And after that, I will present the application of the model, and finally, I will explain the future prospects of our project. Yeah. As you probably know, pulsars are rotating neutron stars, which are compact objects with very small and stable periods, with huge densities and very strong magnetic fields, the strongest magnetic fields we know in the universe. At the present moment, almost 3,000 pulsars have been detected. We know almost 3,000 pulsars, and most of them are detected in the radio band, but some of them, around 200, are also detected to emit gamma ray radiation. These are the so-called gamma ray pulsars, which are mostly detected by the telescope. Out of these, some of them, around 40, also emit non-thermal X-ray radiation, and these are what I will call the high energy pulsars. Some example of these are the crack pulsar, Vela, or Gemini. Now, the high energy emission of pulsars is considered to be produced in the magnetosphere of a pulsar. The magnetosphere is the region embedded in the neutron star where a dynamically relevant magnetic field develops. This magnetic field is considered generally to be a magnetic dipole, but in reality is more likely a multipole. But this dipolar approximation has turned out to work quite well. In this region is filled with charged particles which form a magnetized plasma, and this magnetized plasma corrotates with the neutron star up to a point at which the corrotation speed equals the speed of light. This one is the light cylinder, and this light cylinder, the magnetic field lines open up, get twisted, and probably undergo magnetic connection. The magnetosphere is generally assumed to be under the so-called force-free condition, in which the Lorentz factor acting on the charged particles vanishes. And these charged particles are thus not accelerated and slide along the magnetic field lines and corrotate with the star. However, in some peculiar regions of the magnetosphere, this force-free condition is expected to be broken, when this, probably by instabilities in the plasma density. When this occurs, an electric field parallel to a magnetic field develops in these regions, and the particles entering in these regions can be accelerated. This acceleration of particles is indeed required for this high energy emission we detect. So, in these regions where these regions of the magnetosphere where the force-free condition is violated, particles are accelerated, and thus high energy emission is produced. Now, one of the great unknowns of these magnetosphere studies is where are these regions located. They cannot be located at any place in the magnetosphere, but instead some conditions must be fulfilled, and thus this let us with very few candidates. Historically, the main three candidates have been the model, It's considered that the acceleration region is located between the last open field line and the first open field line, and has an extent of about 1 light cylinder. Another model proposed is the floodgap model, in which this acceleration will be located in the separatrix of the magnetosphere. And finally, the polar cap model, in which the particles will be accelerated in the magnetic pole of the neutron star. And in the last few years, another candidate has gained force thanks to the development of the so-called particle in cell simulation. These simulations simulate the dismagnetized plasma as an ensemble of particles instead of as a fluid, as is done in magnetohydrodynamic simulations, which are the most commonly used magnetospheric simulations. And these particles are simulated together with the electromagnetic field in order to create such consistent magnetospheres. These simulations done across the world by different groups all seem to point to the same places of particle acceleration, namely the Y point and the equatorial transition. The Y point is this point here. This is where the open magnetic field lines connect and undergo magnetic recognition. This magnetic recognition can accelerate particles. So in these places, this Y point and the equatorial transition, particles can be accelerated, and thus energy emission can be reduced. Another relevant aspect about this high energy emission is which is the radiation mechanism in action in these regions. So which is the mechanism producing this radiation. For the energy band between 1 GeV and 10 of GeV, so in X and gamma rays, and the three main candidates are synchrotron radiation, curvature radiation, or synchro-curvature radiation. This last one is the one in which we focus, that we consider in action, and is emitted by the charged particle moving in a magnetic field line, in a curved magnetic field line, and spiraling around. The exact nature of the emission is determined by the perpendicular momentum of the particle. So it is helicoidal movement. So if the perpendicular momentum is huge, the synchrotron losses will be relevant, and the emission will be limited by synchrotron radiation. On the other hand, if the perpendicular momentum has been totally lost and the particle slides parallel to the magnetic field, the radiation will be dominated by curvature. In the situation in between, in which there is a perpendicular momentum that is not very relevant, the emission will be purely synchro-curvature. And for higher energies, above 10 GeVs and up to 50 GeVs, the main candidates proposed are the intercontinental scattering or synchrotron set control. Now, I have said what we are considering is the synchro-curvature radiation. So we base our model on this kind of radiation. Our model relies basically on three effective parameters: the parallel electric field in the region, and an effective length scale of the emission region, and the local strength of the magnetic field in the region. With this effective approach, we are able to reduce the complexity of the problem to only three parameters, which make our model much more easy to handle and much more agile to use. What we do, first of all, is to compute self-consistently the dynamics of an ensemble of charged particles moving along magnetic field lines in these acceleration regions. And we consider that all the particles travel back in the backward direction, so exiting the neutron star, and all are born with the same Bethe properties, namely an initial value of the Lorentz factor of 1000 and an initial value of the pitch angle of 45 degrees. The pitch angle is the angle between the direction of motion of the particle and the direction of the magnetic field. Now, we characterize our acceleration region by effectively parameterizing two relevant quantities: the curvature radius of the magnetic lines in the region and the local strength of the magnetic field along this region. We do so with this two parameterization, in which this parameter V is the so-called magnetic gradient and is one of our three parameters. Once this parameterization and the initial conditions are established, we let numerically evolve the ensemble of particles along the region with the evolution ruled by this equation of motion, in which this term is the radiation reaction force that accounts for the synchro-curvature losses that suffer these particles when they are accelerated by this electric field. This parameter that I will call a parallel is another of the three parameters of the integral. Then, in this way, with this equation of motion, we get the evolution of some evolution along the region of some relevant kinetic quantities. For instance, the Lorentz factor of the particles is you can see here how with distance they increase, so particles are being accelerated, and as the Lorentz factor increases, and also the Fields angle, which as you increases with distance, meaning that the perpendicular momentum of the particles has been lost, but it's being lost due to the loss of perpendicular momentum due to synchrotron losses. Now, having the evolution of this another kinetic quantities allows to compute the curvature power spectra of a single particle at each position of the trajectory. This is done by means of the SYNCHRO-CURVATURE formalism, which was introduced in 1996 and reformulated here at IFE 2015. And this is the expression for the SYNCHRO-CURVATURE power spectra for a single particle. And this reformulation here introduces a key parameter, the so-called SYNCHRO-CURVATURE parameter, which indicates the nature of the radiation, that is, whether synchrotron or curvature is eliminated. For large values of these parameters, synchrotron dominates, and for small values of this parameter, the curvature is the dominant radiation. You can see here the evolution of this parameter along the region. So at the beginning of the region, this parameter is large. So in the inner parts of the trajectories, the dominant radiation is synchrotron, while in the outer parts of the trajectory, the dominant radiation is curvature. And in between, we have this transition region in which the emission is purely synchrotron. Well, these are the magnitudes in this spectrum. And in order to account for the diversity of magnetic field lines and of trajectories present in the region, what we are doing is giving a weight to the contributions of each of the points in the trajectory. In this way, what we are doing this with this effective particle distribution. And in this way, we are reducing all the complexity of the real scenarios and some physical ingredients that we are not considering, and we are able to contain all this complexity in one effective particle distribution, and this one parameter is 0, which contains all this complexity. This parameter, in the context of this particle distribution, indicates the grade of uniformity of this distribution. So for small values of this parameter, more weight is given to the inner parts of the trajectory, while a larger value of this parameter indicates that the distribution is more uniform along the acceleration region. Now, one physical ingredient that has been newly introduced in the last year is a different treatment of the injection region. What was done so far was to consider that up to an extent of 10⁻⁴ light cylinders, all the contribution from all at each position, the spectral contribution was dominated by the Birth properties of the particles being injected at each one of these positions. But what we do now is to consider properly the trajectories of all the particles, so that at each position of this so-called injection region, there is not only the contribution of the particles being injected there, but also the contributions from the particles that are injected at inner positions in the trajectory. So there is at each position there is a contribution from the particles being injected there, and the contribution from all the particles being injected at the earlier positions. To account for this effect, we introduce another way, and we convolve the single particle our spectra with this wave, and after that we convolve this spectra with the effective particle distribution that I have mentioned now. And now I forgot to mention about this N0, which is a normalization of the particle distribution that is simply as a scaling factor and is found analytically. So when we convolve the spectra with these two waves, we obtain the total power spectra emitted by the whole region. So the total spectrum is this one, and this spectrum, this X0 is another of the three parameters. So this spectrum is ultimately defined by only three parameters: the E parallel, X0, and the magnetic gradient B, and this normalization, so that we are able to describe the spectral energy distribution of a particle, of a pulsar, with only three parameters and normalization. Now, in order to compare our spectrum with the real spectrum, so to assess how similar are the spectra produced by our model to the observational spectral energy distribution of pulsars, we have to confront our model with real data of high energy pulsars. We do so by fitting the population of high energy pulsars with our model. We do a systematic fitting that of all the population thanks to the effective approach that allows to constrain the parameters, the model parameters for all the parameters. In order to assess how good fit is, what we do is to consider the statistical chi-square reduced, in which this is the observational luminosity and this is the error of the observational luminosity, and this one is the theoretical luminosity produced by our model. The first one of these spectral fittings was done in 2016, in which a sample of 87 gamma ray pulsars with good data were fitted with our model, and the model successfully resembled these spectra quite good. These are some examples of the spectra of the fittings back then. And also in this paper, there was a study of the correlations between the model parameters and some trivial properties of the pulsars, and getting these two correlations, an anti-correlation between the two model parameters E0 and E parallel, and also this correlation between the parallel electric field and the strength of the magnetic field and the light cylinder. After that, in 2018, the model was extended to include also the X-ray radiation. That is, that with our theoretical spectrum, we could reproduce both the X-ray and the gamma ray spectra, the gamma ray band, sorry, spanning 8 orders of magnitude. Then again, in 2019 was done a spectral fitting of the pulsars possessing both the gamma ray and X-ray data. And this spectral fitting has been repeated now this year with the same results and a little slight improvement. And in this fitting, the majority of the pulsars were reproduced by our model. Majority of them, so these are some examples. Well, both bands are reproduced quite well by our spectra. And this is remarkable because a few of the radiative models that exist are able to reproduce both bands at the same time and with a single radiation mechanism. However, not all the pulsars were well fitted. Some of them, the model was not able to reproduce exactly the data. Here. And for these cases, it was proposed an extension of the model in which instead of considering one acceleration region, two acceleration regions were considered. So that the radiation we detect from Earth is the sum contribution of the radiation emitted from both acceleration regions. This is a schematic representation of how this situation could be, but with this spectral fitting, we are not doing any strong assumptions about it. So we are not getting information about the geometry of the region. So this is just a schematic idea. And with this model, this expansion of the model, the pulsars that were not well reproduced by the model with 3 parameters here, that we call this model with 3 parameters minimal model. So the pulsars that were not well reproduced by the minimal model. Now with this expansion of the model, well reproduced, as can be seen here in some of the examples. Then in the last few months, another expansion of the model was proposed. We asked ourselves if letting the length of the injection region that I have mentioned before as a free parameter instead of fixed could be used to explain the pulsars that were not fitted with the minimal model. So we did so, and for some of the pulsars that were not well fitted with the minimal model were now well fitted. Here the green lines indicate the spectra produced by the minimal model, and the red and blue are the model in which the injection region is left free. Some of the pulsars were well fitted, but not all of them. So that if we were to choose an expansion of the model, we would rather choose the one with 2 acceleration regions instead of the one in which the length of the region is left free. Now let's move to a more numerical aspect of our project. About a year ago, we thought on improving the numerical approach, the numerical procedure that was being used, and we implemented a minimization algorithm in order to directly find the resting parameters of the parameters giving a better fit. The algorithm we introduced was the Nelder method, which is based on the geometrical figure of a simplex. A simplex in 2 dimensions is a triangle, and in 3 dimensions is a tetrahedron. So this simplex is placed in the space of parameters, which in our case are parallel B0 and B. And at each of these vertex can be evaluated the function to minimize. In our case, the function we want to minimize is the chi-square reduce, which you can see here an example of how it looks in 2 dimensions. And so what we want to do is to find the set of model parameters that minimizes its square. In order to find this minimum, this simplex is left to evolve, being iteratively modified with a series of transformations, and is directed through the space of parameters up to the region of the minimum. Here you can see how this evolution goes. The simplex modified, it reaches the region of the minimum, and reaches this region, a species swings, and it finds the minimum. Now, we implemented a numerical pipeline consisting of 3 different steps. The first one was a 2-dimensional Nelder meet, in which a parallel and X0 were left free, and B was fixed to a fiducial value of 3. After that, a 1D section in which B was left free and a parallel and X0 were fixed to the best parameters found, to the best values found here. And finally, a 3D Nelder minimization where all the 3 parameters were left free. We decided for this configuration because with these 2 first steps, we are already close to the region of the minimum. And with this last step, we are fine-tuning the result and assuring that the results found the minimum found is good. This configuration was the better fit between computational performance and security of that the minimum we have found is applicable. Now, with this, this new approach, the computational time decrease achieved as a factor 50, depending on the pulsar. This translated to a feeding time of now 20 minutes, while the previous approach was around 10 hours per pulsar. This numerical approach allows us to get engaged in more computationally demanding studies. For instance, one related to the timing properties of the pulsars. We focus on these timing properties, the period and the period derivative. And we studied how these timing properties affect the spectral energy distribution of a pulsar. So in order to do so, we took a pulsar, this +7303, and we changed its period. So we considered the real period, which is 316 milliseconds, then 50 milliseconds, and the millisecond. For each one of these different periods, we perform a spectral fitting, and these are the results we obtained. For the real period, of course, the fitting was good, but for the other two periods, the best fits found cannot be considered as a good fit. The results show that this is not a really good fit. So what does this mean? The same is observed for the second pulsar, and not that clear as in 007, but okay. So what does it mean? It means that if we do the exercise of not considering the period of a pulsar, and we do a spectral fitting for 3 different values of the period, we are able to say which is this real period. So if we watch these 3 results, we would say that the real period is this one, or at least it is close to this period, because the fitting is quite better in these two cases. So in the light of this, we ask ourselves, can we infer the timing properties of a pulsar from its spectral energy distribution? That is, if blinding ourselves from the timing properties and just considering the spectral energy distribution, we are able to recover the timing properties of the pulsar. So some hints about the real period of the timing properties. In order to ask these questions, we modified our spectral fitting tools in order to deal with the period as a free parameter. To do so, we defined a logarithmically spaced grid of periods from 1 millisecond to 1 second, because this is the typical period range of gamma ray pulsars. And for each one of the periods, we perform a spectral fitting, so that we ended up with a grid of periods, and for each period, a chi-square value. With this, it is possible to draw a chi-square versus period plot, and with this we aim at defining a plausible range of periods in which the real period lies. So this is our goal, to find something like this in which the real period, dashed line, is inside the range. The range is defined with this annealing, which indicates a 1 signal distance from the smallest chi-square, so that all the points below this line are statistically equally good fits. So in this range of periods, we will place on the periods that lie below this line. So notice that if we are blinding ourselves from the timing properties, we are also not knowing anything about the period derivative. So what we did this was to look at the typical diagram of gamma ray pulsars, these squares and triangles, and we saw a kind of correlation, and we did a linear regression in order to have the period derivative as a function of the period, so that for each period of the grid, period derivative, a value of the period derivative could be obtained, and the period of the grid and the period derivative from this expression, the spectral fitting could be on for the period of the grid. When we applied this method to a sample of gamma ray pulsars with data, and what we found was that we could say nothing about the period, so that the period was totally unconstrained, that there exists a clear degeneracy between the period and the one parameters, particularly parallel and zero, so that when changing the period, it was always possible to find a set of parameters for which a good fit could be found. In order to break this degeneracies, we thought that adding the X-ray data, so adding this restriction, could break this degeneracies. And so we took a sample of the pulsars for which good gamma ray data and X-ray data is available, and we applied our method to this kind of pulsars. What we found was that indeed this analysis was broken, and that we were able to define a period range for the real period of the pulsar existed. So these are some of the examples of these distributional ranges. This was done for eight out of the 15 pulsars studied. And for the other 5, the period was still unconstrained, so a plot similar to this was found. Now I will show how this is not what I had in mind. Sorry, I had some technical issues. And so this is how the spectra is modified when the period is changed. So we can see for small periods, the spectra is not very, does not explain very well the data. It stays in the X-ray band, but when increasing the period, approaching the real period of this pulsar, which is 0.350, the spectra better resemble this band. So here the fit is quite good because we are approaching the real period. Notice that in this movie, for all the periods, the X-ray band was well fitted. So what breaks the analysis is adding this X-ray. No. So this is a summary of the study, the application of this method on the pulsars with X-ray and gamma ray data. So around half of them is possible to define a range of around 1 order of magnitude, with some of them larger ranges, and one of them is a very narrow range. So this method has indeed an application, and it is an application regarding the unclassified galactic sources of Fermi. The telescope Fermi, out of the around 6,000 sources that it has detected, 1,000 are not classified, so we do not know what these sources are. Some of them are considered to be pulsars, but it's not sure that they are pulsars. And if for these sources an X-ray counterpart exists, we could apply our method in order to improve the blind period searches on these candidates by defining a period range in which these blind period searches could focus, and in order to assess whether for these candidates there is a pulsar lying in a period lying in this range, so that these candidates are indeed pulsars. By now, there are some classified sources that has this X-ray counterpart, but not all of them. And so our methodology will be much improved when the X-ray or sky surveys of Athena and EXTP are available, because many of the classified gamma ray sources of Fermi will have this X-ray counterpart. Okay. And now to finish this talk, I will talk about I will present the future prospects of our project. First of all, we will revisit some of the current assumptions of the model. As I have said, we do an effective approach in which all the complexity of the real scenario is embedded in just a few model parameters. And now we will use some of these simplifications in order to do our model more realistic, but keeping the number of parameters as low as possible, so keeping our model as easy to handle as possible. Some of these simplifications are considering particles moving backwards, so the direction of the neutrons are going to a neutron star, and also considering an electric field not uniform in the acceleration region, as it is likely to happen. And Then another study is done in parallel to this spectral fitting study. That is the study of the light curves of the gamma ray pulsars. In 2019, it was published a paper, first paper on this topic, in which it was established a geometrical representation of the acceleration loop. Because in our spectral fitting, we cannot say a lot of about the geometry of the region, and by this study, we could obtain more knowledge about the geometry of the region. The SYNCHRO-CURVATURE formalism has already been introduced into this theoretical structure, and some studies have been done. So our plan is to continue with these studies, and in the near future, couple the spectral fitting procedure with this light curve study in order to obtain much more information about the objects we are studying and improve our knowledge about the high resolution of photos. And that's all. Thank you for the attention.
Thank you very much for the talk. Are there any questions? Yeah.
Okay, so yeah, for the question is which is the error in the estimation of the period in this period inference application. So, but we are not giving an exact value of the period. So there is no this error. What we do is only defining a range of periods in which this period may be located. But since all like all these points are below the Zamni limit, we cannot statistically say that some are better than the others. So we are not doing any assumption about the exact value of the period, but instead of giving a range in which this period could be located.
Following up on the question, how accurate is the difficult real period model? And the follow-up question is, how is the real period?
Yeah, sorry. Yeah, okay. Okay, so the question is which is the real period estimated. The next question is that I don't really know because I'm not an expert on this observational site, but I don't really know. I think that it is.
How precise do you know the period of the time? And more than that, we have and then the answer that is you see there it is not bad. You can go from the example to say that and the later is that you have this analysis that you not know if you find the solution. So you need to so basically you have range for the period, and then the last is the period range in which you have to range over finding the period in the lesson is the most valuable. So
very interesting also for research of gravitational waves of what we don't use any other questions? Yes.
Yes. Okay, the question is in this video, well, this is not exactly, but it's similar, that the spectra change abruptly. So this is a result of the model trying to accommodate to increasingly uncomfortable situations. So in here the field is going increasingly bad, and because no other combination of parameters gives a better fit. And at this point, the chi-square radius changes, and another minimum better, so another minimum better to this one appears. So, and then the algorithm points to this other minimum. And we have just like we have like this, and we have the local minimum. So it is really that the function changes, and for this period, I mean minimum appears that was not present in this algorithm. So in the with only a parallel 0 and b, the chi-square function is quite smooth. There is clear value, but when adding the period, this smoothness kind of disappears in some regions. So these abrupt changes happen. Yes, yeah, exactly. Yes, yes, sure. And it's so taking the three parameters of this period on this period gives a worse fit than the rest. And it does all these jumps remain.
Any other questions? Also from Zoom?
In Zoom, any question?
I think there is,
No question.
Actually, I have a question. At present, you are just considering synchrotron and curvature emission. You are not considering of distribution or
No, really. We are just considering synchro-curvature radiation, but this is one of the future prospects for the non-near future, adding this inverse content and self-curvature content in order to explain also this things that appear in the tensor or 100.
but why you have the prediction and the spectral limit distribution?
Okay, yeah, this is perfect because yeah, yes, true. This is consequences or a consequence of this particular distribution. So the basic parameters found for this 0 are rather small, so it means that more weight is given to the inner part of the trajectory. And as we have seen here in the inner part of the trajectory, the radiation is mainly synchrotron radiation. Synchrotron radiation is at lower energies than curvature radiation. So what we have is more important of the inner part of the trajectory. In this inner part of the trajectory, spectra peaking at synchrotron energy. So that's this.
So they are basically synchrotron and curvature.
Yeah, more or less. Yeah. Dominant of one or the other. Sorry, the question was why these peaks appear in the spectral distribution. why these two peaks appear.
Any other questions from the audience here for Zoom? Okay, not we can again, Daniel.